Hello, everyone, and welcome to this exam revision webinar for Mathematics 2. My name is Siri, and it's my pleasure to be here today on behalf of LSE. So as you know, we have a 90-minute session, and we're going to focus on solving exam-style questions. So what I've prepared for us here is a set of precisely that, and I'm going to solve them live using my iPad so that you get more examples of how to structure your answers in the exam. And at the same time, it will allow us to revise many of the key topics in the course. I will also share my slides with you afterwards, and they will be posted to the VLE. So you don't need to take notes as such. You may want to have pen and paper handy if you want to just jot down a few calculations as we go along, but we'll be moving at a relatively swift pace, so there's no need to try to solve the questions as such now. So starting with the first question, we have the supply and demand functions here as given. And it's a three-part question, this one. And it's going to evolve into a question on excise tax. But the first task here in part A is just to find the equilibrium price and quantity. And so this is a system of simultaneous equations that we need to solve. And one way of doing that is to set QS of P equal to QD of P. So equating the two expressions for Q as follows. We see now that if we add 3/4 P to each side of the equation, or if you like, send this, as we like to say, minus 3/4 P to the other side, the P becomes the subject here on the left-hand side, and then adding 1 to both sides of the equation gives us 12 here. And so this is our P star. That's the equilibrium price. And now to find Q star, we just substitute this back into either equation 1 or 2. It doesn't matter because it is a simultaneous system we are solving. So let's say that I use here equation 1. And it's simply QS of P star then, which is P star divided by 4 minus 1. And P star is 12. So Q star is 2. And so this is the values of key. These are the values of Q and P at the equilibrium point. But now the government imposes an excise or per unit tax of T on the market. And we have two tasks here. One is to find the new equilibrium price and quantity in the presence of the excise tax, and then work out what percentage of the tax per unit has been passed on to the consumer. Now, since we're doing revision, I'm just going to write a little bit here. So remember that it's the supply function that changes because suppliers now see an effective price of P minus T. And so the supply function in the presence of the tax becomes the old supply function now evaluated at P minus T. And remember that the expression for the supply function was that Q equals P over 4 minus 1. And so now we get P minus T over 4 minus 1. We simply replace where we see P, we put P minus T. Now, consumers still see a price of P, and so the demand function remains unchanged. And so the demand function in the presence of the tax is precisely the same as before. And now we find the new equilibrium price by solving the simultaneous system of these two equations. So now we could call the equilibrium price in the presence of tax PT star and again we can equate the two expressions for Q. And the first thing we can do here is to multiply both sides of this equation by 4 in order to get rid of the fractions. Then we rearrange this. We get 4P on the left-hand side. And then we get 48 plus T on the right-hand side. And now we divide by 4. To find our new equilibrium price in the presence of the tax. And then we substitute this back into either the demand or supply function. We could say use the demand function here. To see what Q star is. And we see that we are left with 2 minus 3T over 16. And now we want to answer the second part, which is what percentage of the tax per unit has been passed on to the consumer. And so let's look at the new price minus the old price. And so we see that a quarter of T, in other words, 25% of the tax has been passed on to the consumer. Now, as a final part here on this question, we want to write down an expression for the government's tax revenue and find what value of T will maximize this revenue. So what is RT? Obviously, RT here is a function of T. It's T times the equilibrium quantity in the presence of tax. And so we see here that the revenue function is a quadratic here, where the coefficient of T squared is negative. So the graph is shaped upside down like that. But now we want to find critical points of the revenue function. And as you know, critical points satisfy that the first derivative of the function is 0 at the point. And so we differentiate the above. It simplifies like that, since 6 over 16 is the same as 3 over 8. And now we just need to make T the subject here. We can multiply both sides by 8 and rearrange. And we find that the revenue function has a single critical point at T equals 16 over 3. And now we want to argue that this is indeed a global maximum. Now we can look at the second derivative. And we find that this is negative for all T, in fact. And so at the critical point, it is also negative, obviously, which means that this critical point is a local maximum. And since it is the only critical point, it is clearly a global maximum. And now, just a little side note, beyond the scope of the course, but when the second derivative of a function is negative for all t, which is the case in this example here, then that means that the function is concave on its domain. And then that means that any critical point is indeed a global maximum, so not just local, but that's beyond the scope of the course. We have argued it as we just wrote down here. Now moving on to the next question. So we have a linear system here in three unknowns, three equations for three unknowns. Now there is a constant k here appearing in the last equation. And we're told to use row operations to determine the constant k if the value of the constant k for which the system of equations has no solution, a unique solution, or infinitely many solutions. And we're actually given a way that there must be some value of k that gives us infinitely many solutions, because we are asked to write down the solution in vector form for that value of k. So we will get to that soon. However, let's remind ourselves now what this system looks like written in matrix form. Of course, in the exam, it will be fine to simply write down the augmented matrix directly and start doing row operations. So we put in the coefficients of x, y, and z into what we like to call the coefficient matrix. So if we want to give that a name, that will be our coefficient matrix A. Then we have the vector x of unknowns. And then we have the right-hand side B. And so now we create the augmented matrix and start doing elementary row operations. So we have a leading 1 in the first row here. And now we want to create zeros below that leading 1. And that motivates our row operations. If we do row 2 goes to row 3 minus row 2 minus 3, row 1, then this 3 there in the second row will become a 0. And if row 3 goes to row 3 minus 2 times row 1, then the 2 in this third row will become 0. So we're keeping row 1 fixed. And now we simply perform the multiplications. Or the operations, rather. And then we see now that we have a 3 here in the second row. That is our next candidate for a leading 1. So let's create that. And finally, we would like to have zeros above and below the final leading one, and we already have a 0 above, but this k here, we would like to make it into a 0. So if we do row 3 goes to row 3 minus k times row 2, then that will achieve that. And notice that if k is 0, we obviously have not determined yet the values of k here, but if k is 0, then we're just deducting 0 multiples from row 3, so there's no problem with that. So we are covered in all cases. So now we have transferred the k here. It now appears here on the right-hand side of our final augmented matrix. And now we are ready to start analyzing and answering this question. So the first question then is about, is there now any value of k for which this system that we were given in the beginning of the question has no solution? So have a little think about that. What would be the value or values of k in that case? And so what would this final row look like if the system has no solution? Then we obviously have zeros here in the coefficient matrix, the reduced version. But if the right-hand side here isn't 0 as well, then we have an equation of the form 0x plus 0y plus 0z equals something non-zero. And there are no x, y, and z that can satisfy that. So in other words, if minus 4k is not equal to 0, which is the same as saying that k is not equal to 0, then the system has no solution. Sometimes we call that an inconsistent system. What does it mean? We can visualize that in R2. Think of a system of two equations then in x and y, each defining lines, but that the two lines are parallel and intersect the y-axis at different points. So they are not the same coincident line, as it were. Then that system of equations would have no solution because the two parallel lines don't have any point in common. So that's what we mean when we say that the system has no solution. In this case, we don't go to the geometric interpretation, but these are three planes in R3. Each of these equations defines a plane in R3. And if k equals 0, but then these three planes have no common point or line of intersection, or plane if you like. They don't describe the same plane. That could be possible, but that wouldn't be the case. Now, is it possible then for this system to have a unique solution? So the point gives us a single value of x, y, and z, so that the answer here, the solution set, would be a point in R3. So have a look again at our row-reduced augmented matrix and think about whether a unique solution is possible for some value of k. And the answer is that there is no such value of k. And why is that? Well, you can see then that if there were a unique solution, well, then the matrix A would have to be invertible. And that means that when we row reduced here, we would get 3 leading ones. And we don't have that. Clearly, it's not possible. Our second column here is missing a leading one, or as it were, yes, in the third row. So that's not possible. So let's write this down. So we cannot get 3 leading ones. In the reduced row echelon form of A. So A is not invertible. For any value of K. And then finally, is there a value of K for which the system has infinitely many solutions? Well, the question already gives it away that yes, that is possible, and we are going to write out that solution in vector form. But what would the value of K be then? Well, we need to have then a row of zeros at the bottom so that we're not in situation 1 here, where we had an inconsistent system. So for consistency, we need the final row to be all zeros. So if minus 4k is 0, which is the same as saying that k equals 0, then we have infinitely many solutions. And let's write down then what our row-reduced matrix or augmented matrix would look like. And let's circle our leading ones again. This basically means that one of the equations here in the original system was redundant. So some linear, when k is 0, then some linear combination of equations 1 and 2 gives us equation 3. Actually, I just spotted it here. I hadn't looked at it, but 2 times equation 1, if k is 0, is actually equation 3. So 1 times equation 1 plus 0 times equation 2 gives us equation 3. It's redundant, so it just simply falls out when we do the elementary row operations. So that's what that tells us. And furthermore, since we are missing here a leading one in the second column, we can treat y as a free parameter. In more general terms, one of the 3 variables can be treated as a free parameter, but our method here tells us that what is natural, since x and z are leading, it's natural to treat y as a free parameter. Now let's first write out what this augmented matrix here means when we write this as equations. We have 2 equations here for 3 unknowns. First equation is x plus 2y equals 3. That's the same here as we had in the original system. But then the second equation is z equals 4. And now you may wonder, well, how does this tell me the solution to the original system where we just set now k equals 0? What do they have in common? They're clearly not the same equations, apart from the fact that number 1 has stayed the same. But what they have in common is that they share the same set of solutions. And by writing it, by doing row operations, we have simplified the system of equations, if you like, to the bare essentials, where we now can read out the solutions. So as we said, we can let y then be s since it's free, where s is then any real number. And so in vector form, we have the solutions for x, y, and z here as follows. If we rearrange this equation here for x, we get that x equals 3 minus 2y, but we said that y is s, and so x is 3 minus 2s. Y is just s, and z is just 4. And now we can split this out here into a point plus a scalar multiple of this vector, where s can take any value. I'm just using the symbol there for the real numbers. So that is the answer to the final part of this question. Now, moving on to the next question, we have a question on the method of Lagrange multipliers. And we are told here that x, y, and z are all strictly greater than 0. And we need to find the values of x, y, and z that maximize this expression here. So we have a function f of x, y, and z equals x cubed y squared z. But we have a constraint, which is that x plus y plus z must equal m, where m is a positive constant. So first of all, when you see something like this, think of m as simply a given number. So we're solving it for all m, where m is some positive constant, but think of it as given. The first thing we need to do is to write down the Lagrangian function. Now here, you remember this, of course, from Maths 1. But now we just have one more variable here. So the Lagrangian is a function of x, y, z, and lambda. And then we write down the expression for the function we are optimizing, whether that's maximizing or minimizing doesn't matter, but in this case, we are maximizing this expression. Then we write the constraint in the form x plus y plus z minus m equals 0. And we put minus lambda times x plus y plus z minus m here. And as I said in Maths 1, where I always emphasize, let's also write down the system of simultaneous equations that we now need to solve. That gives a very clear setup and shows the examiner that we know what we need to do. And we like to call these the first order conditions. We find all the partial first order derivatives of the Lagrangian and set them equal to 0. And of course, in general, these are functions of x, y, z, and lambda. So in other words, what we're doing is we are finding critical points of the Lagrangian. And so now we need to partially differentiate the Lagrangian with respect to x then to begin with. So looking at the first term here, the power of x cubed comes down, and then the power is reduced by 1. Y squared z stay the same, because remember, we now treat y, z, and lambda as constants. And the other term there involving x is minus lambda x. So differentiated with respect to x, we get minus lambda. And then we set that equal to 0. Now differentiating the Lagrangian with respect to y, we treat x, z, and lambda as constants. So looking at the first term in the Lagrangian, the power in y squared comes down. The new power of y is 1, and x cubed and z stay as they are, since they are treated as constants. And then we have minus lambda y left, so differentiated with respect to y, we get minus lambda, and then we set that equal to 0. Finally, now we do find the partial derivative of L with respect to z. And now finally, we find the partial derivative of L with respect to lambda. This final equation here is, of course, nothing but the equality constraints. If we rearrange it. And now we would like to eliminate lambda from equations 1, 2, and 3. And so I'm just going to save some space here. I'm not going to rewrite these 3 equations, but you can see that we can send the minus lambda here to the right-hand side there in all of these 3 cases, and then we can equate the expressions for lambda. And now we need to simplify this further. And recall, we are given in the question that x, y, and z are all positive. So in particular, x and y are positive. And so we can do the following. There are several choices here, but I'm going to divide by x squared y throughout. And let's see what we get then. So now we have simplified these 3 equations quite a bit. And so these here are 2 independent restrictions. So I can set 3yz equal to xy, that's one equation, and 2xz, sorry, is equal to xy. And just looking at the first equation, then remember that y is positive, so I'm allowed to divide by y. And that will give us that 3z equals x. And looking at the second equation here, well, x is also positive, so we are allowed to divide by x. And so we get that y equals 2z. Perhaps we can highlight these here. And now we can substitute these into equation 4. And we said that equation 4 in simplified form here is just x plus y plus z equals m, but x is 3z, y is 2z. And so we get the equation that's 6z equals m, and so z equals m over 6. Z star, if we like, that's the value of z at the maximum. And then we just go back to the equations above effectively, but let me write it below. So x star is m over 2. And y star is 2z star. So y star is m over 3. And so those are the values of x, y, and z that maximize the given function subject to the constraint that x plus y plus z should equal m. And remember, it's not a surprise that x, y, and z star are all functions of m because we didn't specify the number m here. But remember, think of it as given. If we now say that x plus y plus z should equal 1,000, well, then we have already solved it. We can just plug m equals 1,000 into the expressions for x star, y star, and z star. Now, moving on to differential equations. Suppose consumers anticipate market trends according to the demand function that QD of P of T equals 8 minus 2P of T minus 2P prime of T plus P double prime of T, and the supply function is QS of P equals P minus 1. The first thing we want to do is to use the condition for equilibrium to find P of t, given that P of 0 equals 1 and P prime of 0 equals 2. And once we have found that, we are going to describe the behavior of P of t as t increases. Now we know that at equilibrium, we have QD of P of t equals QS of P of t. And so we write down the given information. And then we rearrange. We want to start with the P double prime, then the term for P prime. Then we have minus 2 P of t, but we also have P of t on the right-hand side. So we get minus 3 P of t. And the constants we can put on the right-hand side. And now we see that we have here a non-homogeneous second-order linear differential equation with constant coefficients. And so now we're going to solve that. And I'll refer to it later as well. So let's give this a little, let's call that a little star. I just have a small head start on how you would progress to solving this equation. The first thing we do is to write down the auxiliary equation and find its roots. And this here factorizes nicely, but if you can't spot it, then just use the formula for the solutions of a quadratic equation. We see here that the roots are 3 and minus 1 respectively. And so the so-called complementary function is P of t equals a times e to the r1t. So that's 3t plus b times e to the r2t. So that's minus t, where a and b are arbitrary constants. And then for a particular solution, since the right-hand side here is a constant, we try P of t equals c, where c is a constant. And with P of t equals C, P prime of t is 0. And P double prime of t equals 0. And then we substitute that back into the differential equation. Now, obviously here we get 0 minus 2 times 0. I'm just writing that down so that the substitution is very clear. And then we get minus 3c, and that's equal to minus 9. And so c is 3. And our particular solution is P of t equals 3. And now we know that the general solution then is the complementary function plus the particular solution. Where, of course, A and B are arbitrary. Now let me call this double star here. We're going to refer to this again as well. So we have the general solution, and now we would like to apply the initial conditions. So P of 0 equals 1 and P prime of 0 equals 2. And so we're going to need P prime. So let's start by differentiating. See, let's give that a color as well, just so that it's clear. That will be our 3-star equation. And now we see that using P of 0 equals 1 in the general solution, gives the following equation. So e to the 0 is 1. And so rearranging this, we have that a plus b is minus 2. So that's our first equation in the system. Now using P prime of 0 equals 2 in our expression for P prime above, and so that gives us the second equation in this simultaneous system that we now solve to find A and B. Now it's simple to see here that we can add 1 and 2 then the b terms vanish there, and we get 4a equals 0. So a equals 0. And now substituting that into either equation 1 or 2. And we see that b equals -2. And finally then, we can write out the required solution. And so that's the first part of the question answered. And now we want to describe the behavior of p of t as t increases. So let me just have a look at it for a moment. Remember that e to the minus t is the same as 1 over e to the t. So this p of t here can be written as 3 minus 2 over e to the t. And then we want to see what happens to this expression as t gets larger and larger. And as t increases, the term minus 2 e to the minus t increases to 0. And so p of t increases to 3 as t increases. Another way to see it is that this 2 times e to the minus t here, which is the same as 2 divided over e to the t, well, that gets smaller and smaller since as the denominator grows as t increases in value. So we are deducting something from 3 that gets smaller and smaller. And so the value creeps up towards 3 as t increases. That's another way to see it. Now, let's move on to a question on diagonalization. The first task here is to find the eigenvalues of this 2 by 2 matrix and an eigenvector corresponding to each eigenvalue, and hence find an invertible matrix P and a diagonal matrix D such that A equals PD P inverse. So take a head start in finding the eigenvalues of this matrix. So there is an equation that we need to solve. And what we solve is the determinant of the matrix A minus lambda times the identity matrix is equal to 0. So if you stop to think what that means that this matrix here, A minus lambda I, is not invertible because it has determinant 0. Now that will be relevant as we proceed to finding eigenvectors. There is a reason why precisely this is the requirement. So now then we deduct lambda from the diagonal of A, find the determinant of that matrix. So for a 2 by 2 matrix, that's given by multiplying the diagonal entries minus the product of the off-diagonal entries. So we immediately get plus 2 here. Set that equal to 0. And after pulling this all together, we're left with the following quadratic equation in lambda. And we need to find the roots. And if you can spot them, that's fine. If not, just use the formula for the solutions of a quadratic equation. And we see here that we have lambda equals 2 and lambda equals 3 are the eigenvalues of A. Doesn't matter what order we put them in. Now for each of these values of lambda, we need to find a corresponding eigenvector. Now let's remind ourselves what an eigenvector satisfies, which is the following equation, that the matrix A times X equals lambda X, where lambda is some real number, and the vector X is not the 0 vector. So an eigenvector cannot be the 0 vector. So in other words, the matrix A stretches an eigenvector X by a factor of lambda. So to find eigenvectors then, starting with the eigenvalue 2, we now solve this equation, A times A minus 2 times the identity matrix times a vector X of unknowns equals the 0 vector. And now remember, we know that this has non-zero solutions for X because we know that the determinant of A minus 2 times the identity matrix is 0. So this matrix here, A minus 2i, is not invertible, as I mentioned at the beginning. Because conversely, if it were invertible, well, for a homogeneous equation, then the unique solution of that equation would be that X is the 0 vector. So that's not the case we're in. We know that this has infinitely many solutions. In other words, a line in R2 of solutions. And so writing out this system then, we deduct 2 from the diagonal of A. course, is a system we are solving. And it's not a surprise to see that indeed the second equation here is a scalar multiple of the first. So if we did row operations here on the augmented matrix, we would get a row of zeros at the bottom because the system is consistent, and there we can treat y, for example, as a free parameter. So there are infinitely many solutions as we expect. And so we can simply select the first equation here, keep one of these equations. And this tells us that y equals x. And so we can take any vector of the form where its two entries are equal, as long as those entries are non-zero. So let me call this eigenvector v1. And so 1, 1 appears to be the simplest choice. But let me point out here that the choices are infinite. Any vector of the form a times 1, 1, where a is non-zero, will do. And now let's move on then to finding an eigenvector for the second eigenvalue. Now we deduct 3 from the diagonal of A. Again, not a surprise that the second row here is a multiple of the first, if you look at the augmented matrix here. Because that's precisely what we're expecting. And in this case, of course, it's just 1 times, it's the same equation. And so writing out then, say the first equation, we see that y equals 2x. And so any vector where the first entry, or the second entry rather, is 2 times the first entry will do. And of course, non-zero. And let's stop at this point to say that, of course, we should take the time. I'm not going to do it now because I've already done it, but we know how to check our answers, and you should certainly do that if you have time in the exam, but certainly as you're doing revision, so that you get the confidence that you know how to check your answer. So a times the vector 1, 1 should give us what? It should give us the vector 2, 2, because that is 2 times 1, 1. And that's what it means to be an eigenvector of eigenvalue 2. When a multiplies an eigenvector of eigenvalue 2, it stretches that vector by a factor of 2. And similarly, a times 1, 2 has to give us 3, 6, because 3, 6 is 3 times the vector 1, 2. And 1, 2 is an eigenvector of a of eigenvalue 3. So a stretches the vector v2 by a factor of 3, according to this eigenvector equation that we wrote down above. So it's very quick to check our answers. And finally, now we get to the part where we diagonalize a, although what we did above is of course part of the diagonalization process, but now we want to write a as PD P inverse. Now notice that we haven't been asked for P inverse, we just need to give P and D. And I claim that letting P equal this matrix and D equal this matrix with 2 and 3 on the diagonal, then A is the product PDP inverse. And let's talk about how these matrices are constructed. It's not a unique choice I have made here. First of all, we have said that there are infinitely many choices for the eigenvectors here. So in each case, a non-zero scalar multiple of V1 and the V2 would be equally good. But once we then have selected our eigenvectors, how do we construct the matrix P and D? So the matrix P, notice that I have put V1 as the first column in P, and I have put V2 as the second column in the matrix P. Now, once I have committed to that ordering, I have no freedom in how I construct the diagonal matrix D, because now lambda 1 and lambda 2 have to be in that order as I've written here on the diagonal. So notice that because lambda 1 is the eigenvalue corresponding to eigenvector V1, and so that's in the first position, so this lambda 1 has to be in the first position, and then similarly for V2 and lambda 2. So we could also have chosen a different P. Let's call that P dash, where we put V2 as the first column. So the matrix would be 1, 2, 1, 1. But now then, you can guess what's coming. We have no freedom whatsoever in how we construct the diagonal matrix D dash, because now we have to have the eigenvalue corresponding to the first column of our P dash, which is lambda 2, since we put V2 there. And then we order the eigenvalues as follows. So this ordering matters. And if you want, you can check it, invert these matrices P in each case, and then multiply out, and you see that you're going to recover A. Now, that was part A of this question. Now we want to use this diagonalization that we have just done on A. Remember that A was the following matrix. And you can see these coefficients here appearing in this system here. We're going to write that down now. So we want to use the result from part A to find the sequences xt and yt such that this system here below is satisfied, where x0 equals 4 and y0 equals 3. And you can see then that if we let xt be this vector, xt, yt here, then we have a xt equals a times xt minus 1, just remembering here the matrix A that we had before. But we know that we can write A as the product PD P inverse. And now we can multiply on the left here on both sides by P inverse. And now we can let xt equal P times ut, then ut equals P inverse xt. And so the ut equals d times ut minus 1. And now we use our matrix D that we found. And so we have these first order difference equations here. That we can easily solve. Just going to write down the auxiliary equation for each of these. And so the general solution we are going to find ut is a times 2 to the t, and vt equals b times 3 to the t, where a and b are arbitrary constants. And now using xt equals p times ut, we get the following. So that is our general solution. Now we use the initial conditions we are given. To get the following simultaneous system. We get that 4 equals a plus b, and 3 equals a plus 2b. And for instance, if we take the second equation minus the first, then we see that b is minus 1. and then substituting that back into either of the equation. Say the first, we see that a equals 5. And so now we can write out the solution. Okay, that brings us to the end of the presentation. So, like I said, I will be forwarding the slides to our VLE team so that those can be posted on the course page on the VLE. And the recording will be available shortly as well. So with that, I want to wish you a very good rest of your day. Thanks for joining today. And I hope your exams go well and that you've enjoyed the course. And good luck with the rest of your studies here with us at the University of London and LSE. So thanks so much, everyone.